Super. All right. So we'd very much like to say thank you very much to Aleksi Kurkela for agreeing to give us this virtual talk today. Aleksi got his PhD from the University of Helsinki in 2008. He was then a postdoctoral researcher at ETH and McGill before taking a fellowship at CERN and then upgrading to a staff position there from 2013 to 2020. From 2015, Aleksi has been faculty at the University of Stavanger. And in 2019, Aleksi won the Zimanyi medal for, quote, pioneering work on field theory applications to the QCD equilibrium mechanisms tested in heavy ion collisions and to the QCD equation state tested in neutron star mergers. And for folks who may not know the Zimanyi medal, it is the premier medal for theoretical physicists who are under 40. So congratulations to Aleksi for winning that medal. And then we're very glad to have you here today to talk to us about neutron stars as laboratories of the densest matter in the universe. So please take it away.
Okay, so hi, it's lovely being able to give these two talks. I realized that, especially looking at the list of other talks you have had in this seminar, and knowing you guys, I assume that you guys are much more on the heavy ion collision side. And so what I'm going to talk about is a slightly different topic. I'll talk about neutron stars, which are also systems where you have QCD matter in very extreme conditions, and somehow what we can learn about QCD by looking at them. So I was given the task to give two talks. The first talk being for undergrads as a preparatory talk for the talk next week. So that's this talk here. Here I will not basically talk about, well, I'll mention some of my work, but I'll mainly discuss other people's work. I'll talk about the observational status of neutron stars and things like that, and then I will have ample time to put my own work in the forefront next week. So this I'll show a few of my own results, but this is supposed to somehow give you a basic introduction of what kind of physics we can do from the QCD point of view with neutron stars.
And just for point of clarification, you're happy to answer questions as we go along?
Absolutely. And so I have a bunch of slides. If I don't make it to the end, I don't care. I'd much rather have a rich discussion about things that interest you, and I would be happy to have questions, especially from the undergrads, to somehow set up the tone and level to the level that's most useful for you guys. Especially because I'm not advertising my own work here. I don't mind to take this discussion wherever you guys want it. I should also make a disclaimer. I'm a theorist and I'm going to talk about observation, so I'll probably say everything wrong. But at least you will get a snapshot of what a theorist working on these things that these observations are about. Okay, but let me start with a little bit of an introduction to things. So I assume every one of you knows what QCD is. QCD is the theory governing the strong nuclear interaction, one of the four basic forces in the known world. And QCD tells us that the elementary building blocks are not neutrons and protons, but neutrons and protons are made out of smaller elementary particles called quarks and gluons. So here is a cartoon of what a proton is. Proton is kind of a bag of many quarks and gluons sitting in there. And the dynamics of these quarks and gluons, they tell us what kind of behavior our protons and neutrons and other hadrons are. The QCD has this funny feature that if you try to pull a quark out of a hadron or a gluon out of the hadron, unlike when you pull an electron out of an atom, if you pull an electron out of an atom, then the force gets smaller as you go farther and farther away. But QCD is slightly different in that. And what happens is that if you try to pull up a quark from a neutron away, what happens is that there's a constant force that pulls you back, that really doesn't want to go away from the hadron. And that force is roughly 130 kilonewtons, or in particle physics terms, 400 MeV squared. So 130 kilonewtons is basically the weight of an African elephant. So you can imagine that all of these quarks are confined into these hadrons by a weight of an African elephant. So that's why we call this the strong nuclear force. Now, of course, something happens if you keep pulling the quark farther and farther away. You put more and more energy stored into this string here that connects the two bits, and eventually what happens is that when you keep pulling this quark away, at the end of the day you don't get a broken neutron and a quark, but what happens is that you start pulling anti-quarks and quarks out of vacuum, and at the end of the day you don't have a broken neutron and a quark, but you will have a proton or a neutron and another hadron, in this case a pion. So in this sense, these quarks and gluons, they are always hidden, or the operative word being confined into these hadrons, which are bags of quarks and gluons. Okay. That is, unless you look into systems which are truly extreme. So if you take these bags of quarks and gluons and you expose them into completely extreme environments, like heating them up into temperatures that you have so many of these that they start overlapping, or if you compress them so close to each other that they don't anymore fit into the space and they start overlapping, and then what happens is that there is some kind of a phase transition from a matter that is made out of hadrons to matter that's made out of quarks and gluons. And this is what we call quark matter in this right side, or quark gluon plasma, depending on a little bit on the context. Now, we live in a especially privileged time in the study of quark gluon plasma, or quark matter, because we have fantastic experimental and observational situation right now. On one hand, there is the precision frontier, where you create quark gluon plasma, hot quark matter, in accelerators and colliders. This is a picture of an event happening at the LHC, and at the LHC we create this hot quark matter in heavy ion collisions by colliding two lead nuclei at ultra relativistic speeds together. You create this blob of hot quark matter that persists for a very, very short time until it cools down, and all the particles that were created in that fireball fly to the detector. And this experimental program is quantifying the properties of quark matter in a completely unprecedented detail and precision, pinning down the properties of hot quark matter. And I assume that you guys there know everything about heavy ion collisions, because I know you guys. But in addition to this precision frontier here, we have a new discovery frontier that comes from neutron stars. And what makes this somehow really topical is that in the past years there has been a complete revolution in the in the observations of neutron stars, brought of course most famously by the gravitational wave and multimessenger observations of mergers of neutron stars by the LIGO and Virgo collaboration. But at the same time, there has been a huge improvement in more traditional neutron star observations using radio telescopes and X-ray telescopes, and all of these things give us a completely unprecedented view of this cold, compressed, extreme QCD matter that lies in the cores of these neutron stars. The way this is somehow usually depicted is in terms of this phase diagram of QCD at low temperatures or low baryon number chemical potentials. If you remember from your thermodynamics course, chemical potential is a variable that is related to density. It tells you how much energy you need to use to add another, in this case, baryon in your system. Obviously, when the system is more dense, you have to pay more energy, and that's why baryon number chemical potential corresponds to larger baryon number densities. That's just the variable that's oftentimes used in this context. So this is a phase diagram as a function of temperature and the baryon number chemical potential. So you can think it roughly as a function of density. And we know something about this phase diagram. We know that at small densities and small temperatures, matter is made out of hadrons. We know because of the asymptotic freedom property of QCD, we know that if you go to extremely high temperatures and densities, you will have matter that is quark-gluon plasma. But we don't necessarily know anything else. We know at the zero chemical potential region that the phase transition is crossover. This happens. This we know because we can do certain theoretical calculations in lattice field theory at zero chemical potential. But what is the form of the transition and where the transition happens at higher chemical potentials, we do not know, and that's somehow one of the big questions of people studying thermal QCD is to understand what is the phase diagram of QCD. From the empirical point of view, we can study using different systems and experiments this phase diagram using various colliders. Going down on energy corresponds to going down on going up in chemical potential, and roughly LHC lives here with zero chemical potential, and certain experimental programs in RIC, the beam energy scan goes lower down in the higher up in density, and there are new experiments under construction that will perhaps study this phase diagram even at lower temperatures and higher chemical potentials. But if we really want to go to this limit of cold QCD matter, then our eyes turn from laboratories to the skies, and what we want to study then is neutron stars, which live somewhere here. We don't know if they, on which side of this demarcation line, this red line they are, but that is really the question that I'm interested in. What I would like to understand, that do you reach this quark matter phase in the cores of neutron stars or not? That's somehow the overarching question that I have in my personal question in this matter. Are there any questions or reflections at this point?
Yeah, go ahead.
Yeah, so usually in the most cartoonish version of the phase diagram where we're guessing, usually at these low temperatures and high barrier number chemical potentials, we get the superconductor phase. Compact stars touch that at all? Is there reason to know that they do not, or that they do?
So we don't even know if we are in the quark matter phase. Now, if you're in a superconducting quark matter phase, that's a level of sophistication that we currently cannot even seriously consider. But this is absolutely an interesting question. There are further details to this picture that one can certainly consider. But I think if you want to be in a color superconducting phase of quarks, as oftentimes one talks about the color superconductivity, then we better be on the right hand side of this plot. And because even that question is completely open at this point, I don't know if we have color superconductors in the star. But it is absolutely a fascinating question.
Okay, thank you.
Okay. So that was somehow the introduction to QCD. And let me give you now a small introduction to neutron stars. So when a star dies, runs out of fuel, what happens is that, well, what happens depends on how big the star was to start with. If the mass of the star is less than 9 solar masses, roughly, then what happens is that the star cools down into a white dwarf, which is itself is a very interesting and extreme object, which is kept stable by the electron degeneracy pressure. But if the mass of the star happens to be higher than that, then it's possible that it blows up in a supernova. And then you have two options that what can happen. What can happen is that if the mass of the star is large enough, then you create immediately a black hole. But if the star is a little bit less massive than, say, 20 solar masses, there's a typo that should be mass less than 20 solar masses, then it's possible that you create a neutron star. This picture here that you probably have seen before is a picture of the Crab Nebula, which is related to a supernova that blew up in what 1045, was seen as a bright element in the sky by Chinese astronomers. They recorded it, and we know that this comes from there. It's a supernova that took place in the same spiral arm in our galaxy that we are ourselves. And what you see here is the planetary nebula that came out of that. So this is the outsides of the star that were blown up into the sky. This is expanding like crazy. The speed at which this thing is expanding is roughly 1,500 kilometers per second. So what 0.5% of the speed of light. And of course, this nebula is not the object of interest, but what is the object of interest is what's here in the center of this nebula, where you have this object here. This is now an X-ray, a combined X-ray and optical and infrared picture of what's sitting in the center, and there you have this small object, which is the neutron star, shooting a jet out of it here. And that is the neutron star sitting at the core of this nebula. So what are the properties of these neutron stars? So first of all, they are extreme. So their mass is of the order of 1 to 2 solar masses, and you compress these 2 solar masses into a sphere whose radius is 10 kilometers roughly. So they are extremely compact objects. If you just somehow play with these numbers a little bit, you get a number which is 10 to 17 kilograms per meter cubed, just by taking the mass of the star divided by the radius of the star. That's a number that actually tells nothing to me because it's so large. but if you convert it into something that's more legible, you can convert it into pushing the mass of the Earth into, I don't know, is that a size of a football stadium or something? So into 200 meters cubed volume. Or perhaps more interestingly, the density is roughly that, or the mass over volume is roughly the mass of a nucleus divided by the volume of a nucleus. So the order of magnitude of the average density in a neutron star is similar to that of atomic nucleus. So in some sense, this is the reason why we call these objects neutron stars, because the rough density, average density is related to that of nuclear density. If they were nuclei, they would be nuclei with atomic number of 10 to 57. That's the number of baryons you have in a neutron star. Okay. But we don't really know what's inside the neutron stars. Here you have a cartoon, not in scale at all, cartoon of what we somehow expect to be the structure of neutron star. We're going to talk about the structure a bit more. The only thing what I want to emphasize here is that you reach very high densities. You don't know how large densities you reach because you need to have a model of the neutron star, and we don't currently have a extremely good model of a neutron star, but you need a model of the neutron star to know what the density is. But the density range that you reach is up to, according to this cartoon, up to 15 nuclear saturation densities, where nuclear saturation density is the density of baryons inside large atomic nuclei. So roughly 10 to 44 baryons in a meter cubed, in a cubic meter, or perhaps more usefully 0.16 baryons per Fermi cubed. Sorry, there's another typo. To be Fermi cubed, volume is measured in meters cubed, right? Okay. The only thing what I want to somehow emphasize here is that the densities that you reach are certainly much larger than the nuclear densities. And the other thing what I want to emphasize here is this large question mark, which says that we really don't know what's happening there. We know that we know of many neutron stars. We know of some 2,000. We know some 2,000 neutron stars, pulsars in the sky. They are almost all of them in our own galaxy. Here is a small part of them showing where the neutron stars are. They are basically wherever we have normal visible matter anyways. This is just a small slice of the pulsars we know that are between 6,000 and 6,500 light years away from us. So I suppose one of these is the Crab Nebula as well. They sit in the galaxy. They are in the globular clusters. We know a few in the Magellanic clouds. So there's a large number of pulsars that are there, and one can observe. And one observes them in different ways. There's radio observations of these pulsars, so that's a radio measurement. I mentioned already earlier, we now have X-ray measurements of these stars. They're very extreme objects, so they emit X-rays. And of course, we have the gravitational waves that are, of course, very interesting right now. Is there anything, especially the students, would like to ask at this point? So what sets this somehow structure of these stars is a competition between two things. On one hand, the gravity tries to pull the neutron star into a black hole, and at the same time, there's a pressure coming from the interactions of strong interaction, and that pushes back. And so because of this competition, the star eventually settles into a hydrostatic equilibrium where it can be in a equilibrium state. In the simplest form of modeling, this competition is captured by the Tolman-Oppenheimer-Volkoff equations. That's just the Einstein's equations in a spherically symmetric system with some matter. Well, this here tells how the pressure changes as a function of the radius, and this equation here tells you how much mass you have inside some given radius. And if you pick up yes, so that describes the gravity, and where the information about the strong interactions comes is that in order to complete these equations, you have to find a relation between the pressure and the energy density appearing here. And what that equation of state, which that carries information about the material properties inside the star, tells how easy it is to compress the matter. And so if you have the,
how do we think about this dPdr? So dmdr, I see, I integrate that, I get the mass. And I guess I integrate the P with respect to R, or dPdr with respect to R, and I get the pressure. And at some point, the pressure is 0, but I don't know the pressure at the inside. Is that sort of how I should think about this?
That's a good question. So in order to figure out, if you want to build a star, so you start with these equations, you complement them with the equation of state. And then what you do in practice is that you say that the central pressure is something. And this mass here, that's actually mass inside the radius of R. So you know that the initial condition for the mass is 0 because you're at the center, there's nothing. And you pick some central pressure here. And then you integrate outwards until you reach the surface of the star where pressure is 0. And like that, you can build stars. Did I answer your question?
I guess so. So you sort of have a one parameter family of stars that depends on that initial pressure guess. Exactly.
Okay. And that one parameter family looks something like this. So this is a thing called the TOV sequence, where this is actually a collection of many points where I've chosen some central pressure. Here I choose a small central pressure, and I integrate the equations, and at the end I get a star whose total mass is, in this case, say 0.25 solar masses, and the radius at that point is roughly 14 kilometers. And then I repeat the same exercise by having a higher central pressure, and I get a slightly different mass and a radius. And I keep doing this, and I can plot this kind of a line, a TOV sequence, which gives me a relation between the mass and the radius for a given equation of state. And what's in, so there's a one-to-one mapping between the equation of state and such a TOV sequence. You can see that this TOV sequence somehow reflects the material properties. For example, you see that here, if I have small central pressures, I don't reach the nuclear densities, and then this matter is somehow ordinary matter. It's not too compact yet. So when I add more matter to the star, then its radius gets smaller because the gravitational pull gets smaller, but the pressure doesn't increase very much. Until I reach this is roughly where the core becomes has the density of the nuclear saturation density, and then the pressure coming from the fact that the neutrons don't want to sit on top of each other starts to play an important role, and the behavior of this curve changes. This is, by the way, I should emphasize, this is not the equation of state. This is just a model, just showing qualitative features that these equations of states have. But what you see is that this
So just quickly on the previous page, so I'm just trying to make sure I understand what's going on. So these equations here are only have information about gravity, and then the point that, as far as I understand it, is then you say, okay, we put in some equation of state which gives us our relation between epsilon and p, and then
exactly.
Then we solve them. Then we get this shape on the next slide, and then we see if that corresponds to what we experimentally measure.
Right. So that's the hope. And so the main part of the talk will be about measurements of this of masses and radii and other macroscopic properties of the star. That's the idea. The idea is that if we were able to measure this sequence on the sky with good accuracy, we could then reconstruct the equation of state. And like in that sense, these neutron stars are microscopes that map the physics from the 1 femtometer scale to the scale of 10 kilometers. So they have a magnification ratio of 10 to 19. So they should be probably called not microscope, but femtoscopes.
Let's say, how are you extracting the radius and the mass from the previous equation?
Sorry, can you say that again?
How are you extracting this the mass of the star and the radius from the equation?
You mean theoretically?
Yeah.
Yeah. So I take these equations, I solve them with initial conditions, picking up the central pressure. I integrate them with respect to r until my pressure is 0, and that's the point where I read up what is my r at that point and what is the total mass inside that radius r. I should also mention that this is a really toy model of a neutron star, in the sense that real neutron stars, they spin and they can have other effects. This is just the first step that you do in the modeling. You can there's an industry of numerical relativity in modeling these stars with spin, and when they do something more complicated, they have dynamical effects, so they're not stationary and so on. But this is conveying the conceptual idea that you use gravity and the equation of state to make a connection between the equation of state and the macroscopic properties of these stars. Yep.
Curious about the point at which it starts to become fat again, whether
very good. That's the point that I wanted to address next. So for example, so eventually, I mean, gravity is non-linear. So what happens eventually is that the gravity always wins the game. And there will be this point for each equation of state, which gives the maximally massive star. If you try to put more mass into the star, you don't anymore have a solution. a stable solution. And what will happen is that a star that would live here and get more mass into it, it would collapse into a black hole. And all equations of states eventually have this point. That's called the maximal mass, or the TOV mass, the endpoint of this TOV sequence. And that's a very important thing in this talk. Actually, to be more to the point, here is so in this plot I showed one particular model of the equation of state, but you can make lots of models of the equations of states. There's of course no limit to the creativity of theorists. And here there are different models that contain only. It doesn't really matter what these models contain, but just to mention this model here contains only neutron matter, and here you add some hyperons. You have lambdas coming at different densities into the game, and you can see that immediately. Well, what you can see in this plot here is the relation of the given equation of state leading into a different kind of MR curve. In particular, these equations of states, they get softer here at some lower density, and you can see that on the right hand side these equations of states become unstable at lower densities. And this already gives one punchline of the talk, because knowing, and I'll tell you more about these two stars, but these are two stars that are from which the mass has been measured. You can immediately see they exist, and if they exist, these models are slightly under pressure, because according to these models, the most massive neutron star is roughly 1.4 solar masses, whereas we know that 2 solar mass neutron stars exist. So that immediately tells you that understanding something about the macroscopic properties of these stars tells you something about the microscopic properties of QCD. Yeah.
It's very unintuitive to me that these curves on the right-hand side are not monotonic. What does that tell us?
Yeah. Okay. So yeah, that's a good question. So first of all, you should think this actually as equal as radius as a function of mass. But for some reason, the community always draws them like this, and I'm not going to try to change that. But there is this point where it changes, and that is the point where the star becomes unstable. So actually, you can continue finding this continuation to this sequence here, where the MR curve bends down, but these are unstable solutions. So here I cut the sequence at the point where the star is stable, but here these plots have been continued to the unstable region. Here you can do a analysis of perturbative analysis of having a radial perturbation, and you see that if you increase the central pressure, the mass of the star, gravitational mass of the star, gets lower, which means that it wants to keep doing that, and it eventually collapses into a black hole. It's a very good question, by the way. Yes. Yeah.
So the fact that you hit this turning point, or this maximum, is that an input? Is that what you impose on your equation of state, or is it somehow I don't know, it's just a fact, you know?
So for a given guess of an equation of state, so we don't know the equation of state, but we can guess. A theorist can always guess. And for a given equation of state, there is a given maximal mass. So here are 3 equations of states, and their maximal masses are these points here.
Oh, okay, so that comes from that Volkov equation.
Yes. It comes from this equation.
Okay.
What's been literally done here is taken these functions here, plug them into this equation of this TOV equations, made these sequences for each of the equations of states, and they are these 3 sequences. So these equations of states, they predict a particular relation between the mass and the radius. The relationship between the pressure and energy density predicts a relationship between the mass and the radius. And it also predicts many other macroscopic properties of these stars. This is just a canonical example, this MR curve. I'll talk, if I have time, I'll also talk about other properties of neutron stars that we can measure, which are also predicted by the equation of state in a very similar fashion. There's a question.
Hi, I wanted to ask you. So you mentioned that, like, in order to get these TOV sequences, you basically come up with a case for an equation of state, and then integrate your equations to get what you want here. And you made a point that, like, it takes, you have to be creative a bit in guessing a form for this equation. But I'm sure there's some criteria on to say, okay, here's, I come up with a guess, but, like, okay, this is not physical. So how do you know, like, something at least, like, in some sense it's plausible, it makes sense, or you just have to wait until, like, plot something like this, and as you mentioned, say, oh, okay, this one says that, like, the maximum mass that I can get is the neutron stars is less than what we know is true, so we fill this out. Or, like, is there a way that you can right away, when this one, you can say, oh, okay, this is not, like, this doesn't work.
First of all, do you guys have a microphone? The connection somehow is really choppy. It's very difficult to hear the question, but I did hear the question. So what you were asking, if I heard you right, is that what's the limit to the equations of states here? Do we know what's physical, what's not physical? That was the question, right?
Yep. Yes.
What limits? Right. That's a very good question, and that's going to be the topic of the talk next week. But basically, there are models that are based on some calculations of nuclear forces and so on that give us some kind of a range of what we think that is reasonable. That's somehow the first strategy. I actually have a couple slides of that a little bit later, but let me comment on that now. But the other way of thinking about is that there are only very few. You don't want to bias your equations of states with what you believe that you will find, and what you can do is you can just limit the equations of states with very general physics relations. We know, for example, that the speed of sound we know that the equation of state should be mechanically stable, right? That gives us some condition about the monotonicity of the energy density, for example. We know that the speed of sound in matter has to be less than speed of light, because otherwise it would break causality, and that gives us some maximal stiffness the equation of state can have, and so on. So if you want to be very agnostic about this and not rely on models, you can find a somehow limited space of functions that fulfills these criteria. I'll talk a lot about this on Friday. Sorry, next Friday.
Oh, okay. Thank you.
And I'll show a couple of slides in a minute. But before I do that, let me still comment, like, what I started by saying was that I want to understand the phase structure, and now I say that what we can do is we can optimally measure the equation of state. The equation of state is just a function, and while it is a fundamental quantity in QCD, it's still just a function. What I would like to understand is what's happening inside the star, what's the phase. But the thing is that the phase structure is reflected strongly oftentimes in the equation of state. Here I have a very mundane example of the equation of state of water as a function of density. And here is water vapor, and here you have liquid water, and you can see that the equation of state has a shape that by looking at the equation of state you can deduce the phase diagram. So the reason why I'm really interested in this equation of state is not particularly because I want to know this particular function very carefully, but I want to understand the phase diagram. But the phase diagram is imprinted in the equation of state. This phase transition here tells you about the phase transition here between steam and gas. And there's other examples in the context of the hot quark matter in heavy ion collisions, where we know the phase. Yep.
Yeah, in the phase diagram for water, there, what's going on? Why do you? This is like many curves.
So this is just from an.
On the left, sorry. On the left, you have the equation of state.
Right. So this bit of the equation of state here is between the phase transition between the steam and gas. But there's, of course, water is very complicated. It has a complicated phase diagram. But I just wanted to say that there's a special feature in the phase in the equation of state, which can be associated with the phase change in the phase diagram.
Okay, so yeah, so you have a T1, T2, T3. What are these supposed to do?
So these are just from a thermodynamics book, but so these are equation of state as a function of density at fixed temperature. This phase diagram here is in terms of pressure and temperature, so it's not completely clear how they are connected to each other. But what I just wanted to make the point is that the equation of state knows about the phase diagram because obviously, for example, water in a gas form has a very different compressibility as water in its liquid form. And so on. Because of that, the phase boundary here is reflected in this this feature in the equation of state.
I see. Okay. So is do we know anything about like I don't know whether the analytic kind of structure of the general pressure versus density, like was it temperature, like is it? If I know one temperature, can I guess by analytically continuing like?
Look, I don't want to talk about this. What I wanted to show is a mundane example of equation of state being related to a phase diagram. But the details of this question it's not something that I can somehow or want to spend time on discussing. This is from a thermodynamics textbook, but we can have a discussion after the talk. But I wanted to show somehow similarity, though. Here is a feature in the equation of state that has to do with a feature in the phase diagram, and we know there's a similar thing happening in QCD in this small baryon number density high temperature limit. We know from the lattice field theory, we know the equation of state, we can compute it, and we see that equation of state is very well described by models of hadrons at low densities, and it's described by and resembles that of models of quarks and gluons at high temperatures. And what happens is that you have this smooth change from one phase described by hadronic models to a phase described by partonic models. And that here reflects the phase transition that happens in the phase diagram. And that is probably the strongest argument why we believe actually that there is quark matter appearing in heavy ion collisions, because we know that the temperatures we reach are much higher than this crossover temperature around here. And so what I would like to somehow see is a similar kind of logic taking place in the neutron stars. This is something that I proposed in this Nature Physics article here, where if you look at what we think we know about the equation of state, I'm not going to talk about the details where these lines came from, but you can see that if we try to infer the equation of state from these neutron star observations that I'm going to talk about in a minute, you can see that you can perhaps see a structure coming from the equation of state that resembles that of hadrons to a phase that resembles quarks. So that would be a sign of this part of the phase diagram. And interestingly, that kink in this particular work happened such that massive neutron stars are in this quark matter phase. Now, that's not universally accepted statement, and I don't want to justify that, and I don't want to go into the details of how we identified these phases and so on. What I want to say more as a motivation to study the equation of state, because if we can find these shapes in the equation of states, that can give us hints about the phase diagram, and that's somehow my personal motivation in trying to understand the properties of the equation of state. Next week we can talk about all the details and geek out on how to what are the details of it, but I just want to give you the idea of why I personally think that it's a good idea to study these equations of states of neutron stars. Okay, so I see I'm out of time, and I'm just about to finish my introduction. What shall we do? Shall we stop here and take questions, or shall I continue, or what do you guys want?
I think it depends somewhat on your boundary conditions. I'm happy to continue for a bit longer. A few people will have to leave for 2 o'clock.
I'm happy to go ahead.
I think the consensus is keep going, and if people need to sort of phase transition out of the room, then they will dissociate.
Okay, well, very good. I'll continue at least for a while, and if we go below the critical mass, then you just tell me. I'm not offended at all if you cut me off. As I told you, this is not about my work. So let me somehow a little bit more detail tell you what we actually know about the equation of state. So there were guesses there about the equation of state, but we know something about the equation of state. And at the same time, let's look a little bit what the neutron stars are, what their structure is. So here is a picture of a neutron star. That's an artist's rendering of a neutron star is. What you have here at the surface, you see the atmosphere and the ocean of the neutron star. That's a roughly 10 meters thick layer of stuff that's very ordinary. There's atoms, there's ions, there's electrons, there's even molecules there. So this is somehow everyday kind of stuff. And if you keep going deeper, you drill a hole on your neutron star, and then things start to get more interesting. As you go deeper down into the neutron star, you will start to have this kind of matter that white dwarfs are made out of. So what you have is that the electrons don't anymore stay with atoms or or just separately, but they form a degenerate Fermi sea of electrons. And in this electron sea, you have lattice of nuclei. And as you go deeper and deeper into the star, like 100 meters, you start to get more and more neutron-rich nuclei. Here's a plot that I made on seeing what these points here correspond to the onset point where these different elements and isotopes come into the play. Until you reach this magical neutron drift point, when it's energetically favorable to have just free neutrons in the system. So the neutrons don't decay like in vacuum, but they just like to be there. And so after that point, you don't anymore have so much individual nuclei, but you get individual neutrons there and clumps and clusters and so on. And so that's when you've reached the crust here, the inner crust. And and you can, by the way, see this is another example of a relationship between the phase or the physics changing and it leaving an imprint to the equation of state. Here, this is an equation of state. This time pressure as a function of chemical potential here. And you can see that there's a kink in the equation of state because you start having free neutrons. So that there the equation of state reflects the phase of the matter. Okay, so that brings us to this 100 meters depth of the star. Once you have this neutron matter, then the interaction between the neutrons start to be super important, and at that point it gets very difficult. Well, at the end of the inner crust, you are 1 kilometer deep here, and that's the point where you've reached 1 nuclear saturation density or so, maybe half a nuclear saturation density at 1 kilometer. And then we have to use, so until this point, the physics has been known in the 70s, but then you go into physics that's under active research, I would say, and it gets very difficult to know what's happening there. There's sophisticated effective field theory calculations within chiral effective field theory that go a little bit higher densities and make predictions about the equation of states up to 1.1 nuclear saturation density or so. But that is far away from the centers of the stars, which are living somewhere around here. So if you want to model the whole star, you have to extrapolate all the way up to here. Another thing that we know about the equation of state comes from perturbative QCD. We know roughly at 40 times saturation density from perturbative calculations. I've been working a lot of those, and the talk on the next Friday will be about this part, how this part here can tell us something about the densities inside the region in the stars. But that's where we are at. This is what we somehow know about the equation of state from first principles and laboratory experiments. Just one more plot in this topic. I show these are again solutions to the TOV equation, starting with some central pressure or central energy density and integrating outwards. And I just want to emphasize here that these bits here, this magenta line and this green line, there's 3 different models here. These magenta and green lines, they are the bits that we know, where we know that we have the kind of matter that I showed you. We know that there we have neutron matter, and these black and red lines are what we don't know. So when we call these objects neutron stars, that's the bit that we know that contains neutrons, and the rest is what we don't know. So there we can guess, but we don't know. So we know a few hundred meters into the star what's in there, maybe a kilometer. So this is what I referred earlier that I will say something. So if you now want to somehow understand what's happening at these densities, here is again the chiral effective theory predictions, the maximal densities that we know. Here is our QCD. These are the densities reached in the maximal stars. What you can do, there's somehow two strategies. One strategy is the one which I already showed you earlier, which is to make some models, nuclear models based on some assumptions, like I showed that those equations of states. And you can try to guess what's happening inside the stars. And you can go online, and there's all kinds of libraries and databases of these models and equations of states. Having these models is of course important in order to give insight to people who do numerical relativity simulations and so on, applications. And so the logic is that you build various models and constrain the parameters of these models using the observations. Now, there's a second strategy which has become somehow available because we have now this revolution of these neutron star measurements. We have a significant amount of information about these stars, so we don't necessarily need to guess so much. And the strategy is to come back to the question that there was earlier. You can make these kind of large ensembles of equations of states that don't really come from any model. They are constrained only by physical principles of stability and causality and so on. And then you can see which of them are most compatible with the observations, and you can limit them. This is a result of this kind of a statistical Bayesian inference study. These blue lines are random equations of states that I generated, and then you ask which of these are consistent with the current observations of the neutron stars, and you get this red shape here. I'm not certainly the only one who does this kind of inference. This has become a industry, and I think it's very interesting now because now we can actually do this because we have this revolution in these neutron star observations. The next thing what I would have talked are these different measurements that we have now, but do we have time for that discussion?
I'm curious to know how these are measured. Yeah. Yeah. We are jealous. We will take all your time that you're willing to give.
Yeah. I mean, what we can also do is we can next Friday. I mean, I was planning to give like the spiel of the most recent results and what I find most exciting, but we can then of course continue and discuss the more general features. It's really what you guys find most useful. I mean, I know that this is not really your field, so that's
all of these things are good, and I think you're the last speaker for our season. So if you are willing to even go a third talk, we could fit that in. But you have to put healthy boundaries on your own time.
Yeah. Well, let me continue a little bit further now.
All right.
Okay. So here is a list. So now I'm going to talk about these different measurements, and I don't need to be too detailed about them. I'll just talk about a little bit about them. So this is the list of the currently known neutron star masses. So there's around 30 measurements of masses. It's not completely up to date, but it shows you basically what you have. And what you see here is a variety of different kinds of things. You see there's neutron star binaries. So binaries with two neutron stars, they typically always have a roughly 1.4 solar mass. masses. There's X-ray binaries. There are white dwarf binaries. So you have a neutron star orbiting a white dwarf. There's even neutron stars going around main sequence stars. And you can see all of these mass measurements, they come from binaries. And that's because you need the orbital mechanics to find out the masses. So here these measurements are all in binaries. The most important ones here are these two stars that were the two stars that I showed in a previous slide. They are important because they are the most massive neutron stars that have been measured in a reliable way. You see, there's a couple stars which have even higher masses, but they are not. There's no somehow consensus that the systematics of these measurements are under control. But these two stars have been measured in the so-called Shapiro Shapiro delay measurement, which is extremely robust, and that's why these are very reliable stars. So these are pulsar measurements. So you know, neutron stars they rotate like crazy. The highest rotation rates are around 7, even above 700 hertz, meaning that you have a surface velocity which is roughly 1/4 of the speed of light. That's really amazing to imagine that the neutron star is rotating almost, well, at a quarter of the speed of light. And because they have this enormous moment of inertia, you have or roughly two solar masses inside a small sphere. So that enormous moment of inertia makes these the most precise clocks in the universe, more precise than atomic clocks. And that combined to the magnetic fields going from pole to pole, magnetic pole to pole, makes these pulsars, because then you have these electrons that are trapped in the magnetic field lines, and then they make a beam of synchrotron radiation along the magnetic axis. And the rotation axis and the magnetic axis, they don't necessarily line up. So this beam will go around the sky, and sometimes it hits us, and then we see the pulse coming from the pulsar. And these pulsar measurements, timing these pulsars is a truly a precision game. For example, here is a period measurement of one of these pulsars. I think it's this one here. It has a period known to, I cannot even count how many digits are there. It's really amazingly well known. So you have these these objects in binary systems, and as you probably remember from your mechanics course, you cannot determine the individual masses from orbital mechanics of Newtonian orbiting, and so you need to have something more. And in case of neutron stars, this is always some general relativity effect that will allow us to break the degeneracy of the masses. The orbital mechanics gives you the reduced mass in Newtonian gravity, but you need something more. And this Shapiro delay measurement is something like that exactly. So you have this pulsar here, it's orbiting a binary companion, and you need somehow one more fantastic feature in this thing. You need this orbital plane to be completely inclined with us, such that the pulse from the pulsar, the beam goes right through the gravitational field of this companion. So for example, for this star, the inclination angle is 89.2. So it's really edge-on system. And now what happens is that this pulse goes through this gravitational field. It gets delayed because of GR, and because you can measure so accurately this frequency of this pulsar, you can see how the pulse gets this kind of a funny profile, which comes from the time delay in the gravitational field. And that, of course, tells you about the mass of this companion star through whose gravitational field you are going, and then breaks the degeneracy between the stars. And you can very accurately measure these masses of these stars. So that's why we know about this handful of stars very, very well. And these happen to be the most massive stars. So that's a fantastic. Well, there's also Shapiro delay measurements of less massive stars. So maybe that's not a useful statement in any way. But anyways, we know these stars from the Shapiro delay measurements. And here I just wanted to make the point that made earlier, because we know that these stars exist, that immediately tells you that this kind of equations of states are not valid. Just by knowing the star, mass of the star tells us something about the equation of state. Of course, it would be much better to know the mass and the radius of a star. And then you could make much stronger statements about the equation of state. And in that vein, there's been a huge progress in the past couple of years. Yeah, and this goes to the domain of X-ray astrophysics. So here, what you have is a cartoon of there's a neutron star there, and it has a companion here, and it's eating up its companion. It's accreting material on its surface. And so what happens once in a while in this kind of accreting system is that there's enough matter on the surface of the star to ignite a thermonuclear explosion. And that is observed as an X-ray burst. And what happens is that this envelope, what can happen, it can have such a strong explosion that it lifts the surface up. Okay. And if that's the case, then there is a moment in time when the radiational pressure from this explosion exactly counteracts the gravity. And at that point, the radiation, the bolometric flux from that star is related to the radius. Because the flux of photons is related to the pressure, which is related to the gravity at that point. And so then by measuring the flux of photons coming from this explosion, you can, if you know exactly the right moment to measure, you can determine what is the radius of the star. There's a long history of these measurements, and needless to say that they are extremely difficult. They have all kinds of astrophysical modeling. For example, here is a measurement by a collaborator of mine. It looks that it has quite tight error bars, but you should also note that there's this model D, and there's also model A, B, and C, and so the systematics are not as well under control. There's all kinds of systematics coming in. For example, that it's difficult to know what's the exact time to know when this radiational equilibrium is reached. You need to know the distance to the star. If the disk here happens to block the star, you don't necessarily get all the photons that you get, and so on. It's really serious astrophysics, and I cannot do any justice to that field because it really is difficult.
But these bursts are periodic, right? They're regular.
They come. They're not periodic, but they come once in a while. Here is the flux coming one of these bursts. And what's interesting about these things is that if you zoom in the time domain here very, very carefully, here this is somewhere where the liftoff happens. I think the liftoff is somewhere here. Maybe this line is that it cools down later. If you really zoom into this line here, you can see that there's rapid time variation in it. Okay, you see that there's an oscillation in the flux, and that frequency of that oscillation coincides with the rotational frequency of the neutron star. So the model is that there's a hotspot created by this accretion. It's like the inverse of a, well, it is like the aurora borealis hitting the surface here, if you wish, creating a hotspot. And sometimes it's visible and sometimes it's not visible, and that creates this oscillation here. That's the thing that causes this kind of a modulation in the X-ray emission. And again, if you didn't have GR, that would be kind of the end of the story. But what do you do with that? It's really cool, but what do you do with it? But because of GR, it happens that we can see more than 2 pi of the neutron star. We can see a little bit behind the neutron star. And the more compact the neutron star is, the more we can see behind that. And because of this thing, it's not true that this hotspot is half the time visible and half the time behind the star, but it's more than half of the time visible because you see behind the star. And so that affects the timing of the pulse, and it affects the polarization of the light, and so on, so on, so on. The upshot is that the more compact the star is, more effect you get. And so you can use this pulse profiling to determine the radius, because the smaller the radius, the more effect you get from this kind of light bending. And that's been in the past year super interesting thing. Here is the International Space Station here. And in the International Space Station, there's this one block here. That's the NICER, the Neutron Star Interior Composition Explorer. And it's sitting here. It's an X-ray telescope that has a very good timing capabilities that has been used to time these things. And one of the 2 solar mass neutron stars, they've measured the mass and the radius from two neutron stars, one of which is where we know the mass, which is the 2 solar masses. It was one of the what I showed earlier. These are not actually accretion. This is not accretion powered, but it's rotational powered. So the hotspot comes from some magnetic fields or something like that. But anyways, the logic is the same. And so they're modeling these 2 hotspots there, and they time them, and they can put some limits to the radius. This is maybe fair thing to say that this is a lower limit to the radius. These radii are very large that are sitting here, but the lower limit is quite tight. That is because if the radius were smaller than what's here, then you would have large effects coming from GR. And so that's a very interesting measurement here. That was 2001, and it has been a truly a remarkable result. It's very interesting.
So Aleksi, typically, what's the partner that this neutron star is eating up? Is it just a regular star? What's it?
So in the cartoon that I had here, this was a white dwarf here. In this case, I think this is not an accretion powered, but the hotspots have some different way of coming up. I think it's because of the magnetic poles. I'm not sure if it's actually even very well understood what makes these poles. You should ask somebody else what does it mean to be rotational power? Okay, but this has been in the past year a very interesting result, and it says that a 2 solar mass star has a radius larger than 10 kilometers. And that again immediately constrains the equations of state. And so the last category of measurements that I wanted to measure is the binary measurements. So yeah.
Should maybe this be the place that we sort of wrap it up, and then we can talk about binary stars and or mergers the next time? Does that sound good to you? I don't want to take too much of your time.
Yeah, it's completely fine. It's completely fine.
Yeah. No, I think this is good. So we had lots of questions during, but any last questions before?
I have a question, but I don't want to keep everybody here.
No. Let's have one more question.
That's about again, going back to that way that we relate the equation of state and the radius and mass of the neutron star. I'm just curious, as we approach the sort of black hole limit. So for example, there's a inflection, there's a turning point where you said the solutions become unstable, but is there like some point where we've measured a star that is close to this point that has turned unstable? And the second thing would be, we talk about mass and pressure, but if we're talking about a black hole, the idea of mass at the edge or mass as a function of radius is kind of weird because all the mass should be at the center. So is there just completely discontinuity here?
So I'm not sure if I understood the question perfectly, but the Schwarzschild radius of a star, Schwarzschild radius of a black hole of 2 solar masses, I think it's maybe 5 kilometers, so it's somewhere here. So what happens here is that the collapse starts, and then there is a discontinuity. Then you really collapse into a star, into a black hole. So it's not that this point here is a black hole. That's an unstable neutron star that cannot anymore prevent the catastrophic collapse to a black hole.
Is there any data of a neutron star that somehow absorbed too much mass and has collapsed?
Yeah, I don't know. I don't think so. It would be very interesting to see something like that.
Okay.
There's certainly papers like wondering how the equation of state affects this kind of a collapse. But I don't. To my understanding, there is no current measurements that could at least be with confidence linked to an event like that. Like there's all kinds of transients happening in the sky, and perhaps some of them could actually be this, but I don't speak with confidence.
All right, thank you.
Sort of following up, do you know what the smallest, call it confirmed black hole is in terms of mass?
So the smallest neutron stars are 1.4 solar masses. That has nothing to do with the equation of state, but the astrophysical production mechanism of them. Because
sorry,
the white
Aleksi,
dwarf.
Aleksi, maybe I misspoke. The smallest black hole in terms of mass.
Oh, that's an interesting question. What LIGO and Virgo do, I think what they say is that if the object is more massive than 3 solar masses, it's a black hole. and then because at that point you would be a little bit stretched to say that it's a neutron star. There's interestingly this binary merger of a black hole with a 2.6 solar mass object. It seems to me that whenever I talk with people who study neutron stars, everybody assumes that of course it's a black hole, and the black hole people assume that of course it's a neutron star. And so the nature of that object is completely up. It's either a incredibly massive neutron star, or it's like I don't know so well the black hole literature, but there should be a reason why you don't produce these small black holes. So it's somehow a surprise to everyone. Nobody likes it.
Wonderful. That's great for us. Okay, super. Well, again, really appreciate you taking the time. I think I really enjoyed this. I think we all really enjoyed it. So yeah,
Good fun.
yeah, thank you very much.
Thank you, guys. It's been fun to chat with you.
Super. So